this is which?
This is the second episode of the series, The Airplane in the Skies. And today's episode is on aircraft wings and control devices. We'll be talking mostly about the wings.
Well, go.
Hello.
I'm sorry.
Okay.
All right, look up, look up. Smile.
Hello. This is the second episode of our series, The Aircraft and the Skies. In this episode, we'll be talking about aircraft wings and control devices. A lot of the emphasis will be on aircraft wings. As we go into this, I want to bring your attention quickly to the thought of wings. Wings have been around long before there were airplanes. Look, just see the birds in flight, in majestic flight. There's one here that I want to show very quickly to emphasize this point. See this bird? It spreads its whole wings, and when it's spread like that from tip to tip, that's called the wingspan. And it just flies. This is called a gliding flight. That's from nature. Okay? And it's things like this that we look at when we design the devices that will do that. Those things are looked at in nature first, and we say, wow, there's a device, there is a creature that's able to do this. Can we make a machine that can do that? And then the science begins, the applied science begins, and the engineering begins. So the things that we create are usually an imitation of what God Himself has provided for human nature, and we look at this for the wealth of our knowledge and our exploration. So let's look into aircraft wings. We have different wings for the aircraft. What does it do in the first place? The airplane can almost not fly without the wings. The airplane can, I repeat that, the airplane can almost not fly without the wings. Is it possible to fly at all without the wings? Yes, there are things called wingless aircraft these days, but primarily the aircraft needs wings or some kind of device of wings if it's to take the form of the traditional airplane. And so the wings are very important. Not to even talk about the attachments to the wing, just the function of the wing itself. It's a lifting device. Without lift, the airplane cannot stay in the sky. The wing is the substance, is the part of the airplane that sustains the lift that's acquired by the airplane. How is the lift acquired? Well, there are theories, but the predominant theory is the aircraft lift theory, which is basically the airfoil theory. What is the airfoil? Okay, the airfoil is essentially the shape of a teardrop. A teardrop goes down from the face, but if you look at a teardrop and slide it in the perpendicular direction to the direction it normally comes from. A teardrop comes like that, or a raindrop, comes like that to the ground. If you can turn it like that, so that's perpendicular to its natural direction of flow, then that would be the shape of the aircraft with of the aircraft itself. But that's the shape of the teardrop, which is also the form of the wings we have. So a section of the wing of the airplane is what's called an airfoil. And the airfoil theory shows that there is greater speed on the top of the aircraft, or on the top of the wing, and lower speed on the bottom of the wing. The lower speed has a greater pressure. The pressure pushes the upper portion, so the aircraft stays aloft. Yes, there's the power that's provided, but what uses the power to stay steady in the sky is the aircraft wings. And so we'll look at various aspects of the aircraft wing and the different designs of aircraft wing, and hopefully we will have some enlightenment about the wings. And who knows, some of us may go on to start to generate new wings. There's no limit to knowledge, and we may think, oh, they've all been found out, until somebody comes with a new one, and it's just as amazing as the first one that was introduced by the Wright brothers and their colleagues, their counterparts, when they were doing the aircraft. So let us look into aircraft wings.
Stand by. Looking up at the camera.
Welcome back. I started to talk about the wings of an aircraft and the mimicking of the wings of a bird to do the same. The majestic bird that we look at quite very well represents the parts of the wings of an aircraft and how it is designed, at least when it's first started, before we go on to making modifications to the wings of the aircraft. A wing, as we've said, is some type of fin that produces lift for the bird, for the aircraft, for most of the flying devices, even for the mosquito. The function is the same thing. In fact, it has been found out very recently, the research that's done with all creatures, whether they're biological, celestial, a lot of creatures that can be gotten. I think this was a study done in Oxford, and it was found that all these devices could be as small as a tiny mosquito, as large as a whale, use a specific dimension of the span of the wing from the body, and it's about two-thirds. About two-thirds of the span of the wing is what's used in flying. So flight becomes a common phenomenon that unites all these creatures in their obedience to physical law. And they use an appropriate range, a consistent range. And that could provide us something that would contribute to the advancement in the design of wings and flight components of our aircraft. Well, we have different types of wings. Long ago, when the Wright brothers and their colleagues and their predecessors started to design airplane, the airplanes that they designed were bi-winged. They had double-wing aircraft, as is shown here, and that was done because they wanted more lift. And so because lift is a function of the surface area of the airplane, so by having more than one layer of wings, they had more surface area. They also have greater structural strength. So they had greater lift, which is desirable, and greater structural strength. But these were connected by wires, and these wires added to drag. So they had much greater drag. Eventually, progress was made, and a single wing that is thicker than a single portion of the double wings that were made was then devised. So these days we don't have double wings and triple wings anymore. But they did fly. They did fly, and there was a reason for their introduction until better material and better knowledge of the wings were introduced. And here we see from the onset, from the beginning of the wings, the double wings, for example, the triple wings will go along that line back to typical Cessna, which is a common sports utility aircraft these days, then to the big transport airplane with its majestic wing span and just with trapezoidal form of wings. And to the fighter aircraft, delta wings that seem to have no tail at all. We'll talk about tail in subsequent lectures. but it's all wings, and it takes the form of delta. Delta is just the Greek alphabet, the capital Greek alphabet, and that's the form that the aircraft has taken. So we have these different types of wings with their sweeps, and these all perform essentially the same function: to keep the airplane aloft. Bottom line, to keep the airplane aloft. The different forms and different shapes they have because of the addition of landing gear or engines to them, those are necessary paraphernalia, but the primary first function is to keep the airplane aloft for the wings. Okay. Here we have the triplanes, the triple wing airplanes, and the way this was done, when it was first done, is just like a child's play. As you can see from this diagram, it looks like they were just playing. They were building aircraft right at the corner in their house, and building the propeller, which was all wood at the time it started, by the way. And eventually it flew, So you build something like this, which looks like child's play, and eventually you get into the skies. So you get into the skies, then you think of production. And from production, you think of optimization. And before you know it, you're producing and you're selling this device to societies around. So we have the classification of wings. The wings are classified in different forms. They can be classified by wing layers: biplane, triplane, monoplane. They are sometimes classified by the speed realm: subsonic, supersonic, hypersonic. Subsonic is from very low speed, kind of speed you have in your small aircraft, which can be about 350 miles per hour, to a speed of 0.8, the speed of sound, up to about 0.8 the speed of sound. We still call that subsonic, and supersonic is generally 1.2 the speed of sound to about 3.8 the speed of sound is called supersonic. Generally, it's not a hard fact boundary, but that's generally how it is. And hypersonic goes from about that onward to the high end. There's a range about 0.8 to 0.8 m, the Mach number, to 1.2, and that's called transonic, transonic speed range. That's transferring from the subsonic to the supersonic speed range. So that's, and of course, there's the hypersonic one, which is usually greater than Mach 5 or Mach 5 and above. The wings can also be classified based on their geometric shape: rectangular wings, trapezoidal wings, moderate taper, high taper, elliptical wings, delta wings, swept wings, all kinds of wings like that. So those are some of the forms of the wings that we have for an aircraft. Wings are tested before they are used, just like any engineering device, because you don't want it to fail in function. At least you want to minimize the chance of its failing. And there are different ways that they are tested, no different from any other engineering design, but particularly in these, great precaution is taken in the testing of aeronautical devices, because as you know, a vehicle can fail on the road, not desirable, but there could still be some containment. There's almost no containment in the sky if it fails, because there are three-dimensional areas of its failure compared to two-dimensional when it's just on the ground, or when it's even just on water sometimes. So great care is taken, and that's why usually in aeronautical devices there's tighter tolerance made to the manufacture of the components. So one of the ways of testing the wings is in service. So the wing is already built, and then you're testing the prototype to see the performance of it and the reliability of it. This is very expensive. It was what was first done when this business of engineering know-how began, and it is expensive, and so people have moved mostly from it. There's still in-service testing, but in-service testing now will be necessary maybe for just one built prototype instead of 20 built before until they get a good one, because there are many other methods by which the test can be improved before the real one is built and it's used. One of the primary methods that was used before the Wright brothers, by the Wright brothers, and still used today is the wind tunnel testing. About in the 70s, we used to joke in the aeronautical labs. We will say, oh, about 20 years from now, the wind tunnel will just become a repository for computational data and everything. Well, we were wrong. The wind tunnel is as useful now as it was then, and it's actually gaining more use because of the various improvements that are made to it. So the wind tunnel is a very prominent component of testing devices. In fact, a lot of the data that's used today, and many of the data that are used as constants or that are used in equations, they are data obtained from a lot of tests that were done by the wind tunnel. So that's a very prominent component and a very useful part. We will have other times to talk much more about the wind tunnel. We'll just say a little bit about it and now with other things. Another method of testing the wing is by analysis, computational testing. We've gotten data, again, thanks to the wind tunnel, we're able to get some data that we use in our equations. It's essentially a theoretical approach, fundamentally, then some other known data is added to it. So it's a combination of data until we come to a well-proven test result based on past computational methods. And then there's the simulation. Simulation is, in a way, kind of a computational approach, but the wing is essentially provided and electronically done. So we have a soft wing. It's called a soft wing. It's not the hard one. It's not the real wing. It's one that has been generated on the computer, and we do different things to it, and we see what happens in the computer before the real one is built. We talked earlier about the wind tunnel. It's for measuring parameters of flight vehicles primarily, and for the wind tunnel come in different forms. There's the low-speed subsonic wind tunnel. Low-speed subsonic wind tunnel just means a wind tunnel that does not give you results for operations greater than Mach 0.8, because that's the high-end speed for subsonic. In fact, the low speed just goes to about Mach 0.4, and the high-speed subsonic goes closer to Mach 1. That's goes to Mach 0.8, and it will generally start from Mach 0.4 or 0.5, and that's called the high-speed subsonic. And the wind tunnel could be closed circuit or open circuit. Then we have the supersonic tunnel. We have the shock tunnel, and other types of wind tunnel. There's even the water tunnel sometimes. Well, the aircraft wing essentially consists of the following things: the aileron, the flap, and in some advanced vehicles, advanced aircraft, the slat and the slots. And we will show you in the diagram for the aircraft where these function. But essentially, the aileron is a control device, kind of supporting the control devices that are prominent in the tail. It helps the aileron helps in the turning of the aircraft because the correct turning of the aircraft is called banking. It's a three-dimensional turn. You use the aileron in doing that, where, say, one portion goes up and the other wing goes down. The flap is essentially a descending or ascending device in the aircraft. Then the wing, of course, the structural strength is very important. And in the structural strength, a number of things are considered. Is it the high wing aircraft? Is it the low wing aircraft? Is it the mid wing aircraft? Or in very rare cases, is it a wingless aircraft? And there are conditions for the generation of these types of devices. That is, whether we want a high wing or mid wing or low wing, because there's a structural integrity that it has to have with the body of the aircraft, the fuselage of the aircraft. These are the things that are critical about the wings of the aircraft, and we will explore them further as we go on in subsequent series into the details of these component parts. These are just meant for introductory parts, and hopefully you would get yourself interested and familiar with the various terms of them. Thank you. Hello, I'm T. Omiobidi. This is episode 3 of our series, The Airplane and the Skies. In this episode, we will be talking about the control devices further, and that is essentially the tail assembly.
I'm going to sync my cameras with sound.
Okay.
Stand by. Smiling at the camera.
Hello, I'm T. Omiobidi. This is episode 3 of our series, The Airplane and the Skies. And in this episode, we'll be talking about the control devices, that is essentially the tail assembly components of the aircraft. We mentioned a little portion of control on the aircraft when we talked about the aileron and the flap descending and ascending. The flap moves up and down, where for the airplane landing or the airplane taking off, essentially it's rigid otherwise, and the aileron helping in banking of the aircraft. Those attachments we have in the wing, just like we have slots and slats in the wing. They do a little bit of control, but the main control surfaces of the aircraft are found in the tail assembly. The tail is called the control surface of the aircraft. One of the earlier pioneers in aircraft went on and attached a monk, actually, I think. Yes, in Europe, he went and attached wings to himself, and he jumped off the roof. He ended up breaking his legs, and when he didn't die, when they went to him, he said, "Oh, I forgot to put a tail. I should have attached a tail. It would have kept me steady in the air." Well, even then, the importance of a tail was recognized, except in his case, he was going to attach a tail to himself because he attached the wings to himself. But that's just a statement in passing to emphasize the importance of the tail assembly in the aircraft. The tail assembly has several parts. We look at our traditional tail assembly, and the traditional or the conventional tail assembly essentially consists of the vertical tail and the horizontal tail. So you have the vertical tail on top, and you have the horizontal tail below it. And these are the main components in the rearmost portion of the airplane. Well, let's start with the vertical tail. The vertical tail spikes up as we see it in the traditional airplane, and behind it is the rudder that moves like this. Okay. So the airplane is going straight, and the vertical tail, behind the vertical tail, think of the fin of a fish, a big fish, think of its fin. It's the tail portion, except in this case, there's also the vertical portion with it. When the airplane is going straight this way, and this turns the portion that's attached to the rear of the vertical tail, because that moves, the rudder moves. So when it turns like this, what happens is the wind comes and hits it this way, because this is how it was going before, and that's steady. But if it turns this way, it means there's a pocket for the wind to hit. And if the wind hits it that way, guess what? The nose of the aircraft is going to turn. Okay? So if the wind hits it that way, then the nose of the aircraft is going to end up turning that way, too. That way. And if it was to turn this way, and the wind hits it this way, the nose of the aircraft is going to turn into that direction. And this is, it seems very simplistic, but this is how the rudder works. And the rudder is controlled from the cockpit, and this is how it works, the vertical portion. So we say that the rudder handles yaw of the airplane. The yaw is the sliding. If you were ever to catch yourself on a rainy day on the road, and you tend to go like that, that's yawing as far as the airplane is concerned. So the rudder, the vertical tail control surface handles the yaw of the airplane. That's what's used in controlling the yaw of the aircraft. Then the horizontal tail. The horizontal tail has the front portion, which again, towards the end of it has the stabilizer. Some have stabilizer and the little portion called the elevator. Some have the stabilizer and the elevator combined in the rear portion that you can flip up and down. And when you have the stabilizer and the elevator combined, it's called the stabilator. Okay? And that controls the motion of the aircraft in the up or down direction. When the aircraft is going straight, that's called the straight longitudinal motion. Okay, that's its axis of motion, straight axis. And this that goes this way along the span is the axis across for the aircraft, and the up and down is the vertical axis of the aircraft. So the horizontal tail assembly, the elevator, controls the up and down motion of the aircraft about the axis of that's across from its motion, and the vertical one, like we already said, controls the yaw, and so there's a portion that controls the roll also, but we'll talk about that because that comes from the motion of the aircraft under usually gusty conditions. Okay.
Stand by.
Okay.
Clap. Smile. This is a 7.3 seconds. 7 minutes, 7.3 minutes. Smile.
Okay, we have talked about the conventional tail assembly of the aircraft control surfaces. That's the tail assembly. Well, there are two other portions. There's the T-tail. You will see some aircrafts don't have what we call the traditional tail. They have the T-tail. The T-tail essentially means the horizontal portion stays on top. This is typical of the whale. You know, look at the whale in the ocean. You see the big flat portion. It just lifts it up. Okay, but holding the big flat tail up in the mighty ocean is the rigid vertical portion that builds up straight in the whale itself, and that's essentially how the T-tail assembly is. So the T-tail assembly has its vertical tail first on the body of the aircraft, then it has its horizontal tail on the vertical tail, as opposed to the traditional tail, which has its horizontal tail and the vertical tail building on it. So that's the difference. Why would one go for these different forms? Well, it depends on a few things, including the design of the wings of the aircraft, because there's something called downwash from the wing of the aircraft, and if you have a tail, a vertical tail that is close to the downwash direction from the wing of the aircraft, if you have an upper wing aircraft, the downwash can hit the vertical tail, and it causes more drag, so you may not want such an assembly. But these are designed in combination with the other parameters of the airplane, whether you have mid-wing or low-wing aircraft, and the distance between the length of the fuselage, the distance between whether the propeller or the jet engine, because the output, the wash from the propeller or the jet engine goes to the back, and they will hit the tail if the design is not very well choreographed, so that it avoids the tail and therefore doesn't add to the drag. Okay, so these are all devices that are used. But there's one more. There's the V-tail. V-tail, we had the traditional tail, we have the T-tail and the V-tail. The V-tail essentially is taking advantage of the benefits of the traditional tail and of the T-tail. So it can take that advantage, but it's more difficult to design. It's structurally more demanding. It has less stability. It can be done, and it is done. In fact, many years ago, in the early 70s, there was a company in Orlando, Florida, called Birdman Ultralight Aircraft. And the chief engineer for that aircraft was my professor in aircraft stability and control. Still an undergraduate then, I had the good fortune of being given the responsibility to design, to indicate the appropriate tail section for the Birdman aircraft and to design it. And I did. I think I came up with a V-tail. It's been a long time ago, and it's been many decades ago. But the whole stability and control was done, and we chose, I think it was a V-tail that I recommended to my professor. So you have this, but usually the V-tails are not common in large aircraft. The V-tails are found in smaller aircraft designs. But these are the common tails. There are other tails. There's a canard tails. There's the different kinds of tails. But these are the traditional, the main tails that you have in the aircraft, and that the designer looks at when trying to design the aircraft. So it should, once that tail section has been chosen, again, based on the parameters already present for the wing, the position of the engine, because they have to consider the downwash, the effect of the downwash on the tail assembly. Once that has been done, then the parameters for the tail are taking the dimension of the trim tab, the dimension of the rudder, and the extent to which it will sway, it will respond to stability control devices of the aircraft. And there goes the design process of the aircraft. And these are the steps that are taken in ensuring the control of the aircraft is adequate to meet the various conditions for which the aircraft has been specified. So again, the control surface of the aircraft is primarily the tail assembly. That's the main thing to get from this. The control surfaces of the aircraft, or the control device of the aircraft, is the tail assembly. Okay. All right. With that, we will look further into some other devices of the aircraft as time goes on. But now we have looked at the wing that keeps the aircraft aloft, and we have now looked at the tail. So we've essentially looked at the devices that keep the aircraft in flight, in steady flight, and that keep the aircraft going when it performs maneuvers also, because the wing takes care of steady flight and the tail assembly takes care of maneuvers, essentially. So with these devices, we will go gradually and look at other components of the aircraft until we have looked at least primarily at the different functions of the different parts of the aircraft in an elementary way for this series. And then subsequent ones, we'll go into details into each of them. All right.
Give me a clap. Smiling at the camera.
Okay. We want to look in the segments, we just want to look at this again, vertical tail and horizontal tail respectively, and blow up more their respective functions in the whole tail assembly of the aircraft. Again, the vertical tail consists of the front half, and the last half is the movable portion. The front half is the fixed portion, is part of the airplane structure. Not the latter half really, but the tail end of the tail. The whole thing is the vertical tail, but the little portion there that's just cut off slightly, like a vertical rectangular plate towards the end of the vertical plate. It's the rudder, and it moves to the right or to the left. There's a wire in it. The wire stretches, the wire goes to the control in the cockpit, and so the pilot controls it from the cockpit as to which direction he wants to turn, and it does this, and so it keeps the airplane either going like that or going like that, which is called the yaw. Okay, the airplane yaws when it responds to the action of the rudder, and it's one of those components that call for critical detail design, because you don't want to design it such that it ends up on top having a split section, because a split section on top or at any external portion of the aircraft is an invitation for drag and an unacceptable design in general. So the top has to be aerodynamic in shape and cover both the standing tail, the fixed tail, and the rudder portion. So when you get to the top of the design, the rudder portion doesn't go all the way to the top. If the tail assembly goes all the way here, the rudder portion comes up to here, so that there's some kind of cover to it, like an extension of the fixed tail itself, and the rudder ends up here, and the vertical tail covers it all, like a hat. Okay, so the rudder is able to turn like this under the vertical tail and keep it its function. That's the yawing of the aircraft. Again, remember that when the aircraft is turning, and if it turns properly, which it should, what it does is called banking. Banking. The airplane is banking. How does it bank? Well, it's turning vertically and it's turning horizontally at the same time. And the turning is synchronized so that one continues a three-dimensional motion in the turn until you reach the direction you're turning to, and then the airplane stables again. It just returns to its normal flight. But the process of turning is called banking. one of the common things with the novice pilot, probably we all do it at one time or the other when we start flying, is the instructor says turn, you just turn the airplane like that, and you're told, no, you got to bank it, you got to bank aircraft. So guess what? In banking the aircraft, we just flip it like that. So it's neither of those. It's a combination of both. And there's a ball in the cockpit that you look at to know that you're within the range that allows you for proper banking of the aircraft. But that is the vertical tail. Again, in the horizontal tail, after we have the fixed portion. Fixed portion is usually very rigid. I mean, it's so rigid people can sit on it. It's not generally recommended, but it's strong enough to handle a person's weight sitting on it. But towards the end, at the end of the horizontal tail is the portion, depending on which the aircraft design, it can be just one portion. Again, just like a rectangular plate at the end of the horizontal tail design that goes up and down, and those help the nose up or the nose down of the aircraft. If you need to nose up, this will flip this way, and if you need to nose down, it will flip the other way. So, and this is controlled with some aircraft that have in the stabilizer, the stabilizer that does this nosing up and down is done by the effect of the stabilizer in response to the wind. Yeah. But something that also helps further is called the trim tab. The stabilizer, the horizontal stabilizer, does the nosing up and down to a light degree, but fine-tuning the nosing up and down, just fine-tuning it so it's just right, is done usually by the trim tab. And in the cockpit, you control the trim tab until you get it very stable. One of the things that's also common with the green flight students is you roll the trim tab, and before you know it, the airplane is nosing up, and you push it down because you want it to be stable. The airplane is nosing down, so you want to go on a straight flight, but you're here doing this, going up and down, and sometimes you just give up and you look at the instructor. It's like, take over, I'm done. It's very interesting. But these all have functions in the aircraft, and these are all the tiny, intricate parts that come together and make the aircraft function in a way that we can have confidence in it and sit in it and have it take us from point A to point B.